Why are people freaking out about a potential room temperature superconductor? There's lots of reasons, but one of the biggest reasons is nuclear fusion. We'll break down what that means, how it differs from nuclear fission, and the massive implications for your life and for all of human society. So what happened? Earlier this week, a pre-release paper was published on Archive about the world's first discovery of of a room temperature superconductor. And the paper had really compelling charts and data in there. And so the physics community on Twitter and at large was just freaking out about this because this is a groundbreaking discovery. And these would make these potential physicists Nobel Prize candidates. And so because it's so groundbreaking, there's a lot of hype and a lot of excitement, but at the same time, there's a lot of skepticism about this. And so the whole world right now is waiting for another lab to kind of reproduce what this paper said that they were able to produce, this room temperature superconductor. And so we're not sure if it's actually real or not just yet. That remains to be confirmed. But let's talk about why are people freaking out about it anyways in the first place? What's so crazy about this?
It really comes down to all the different applications that a superconductor would allow for. So right now, there are superconductors, but the problem is you have to have such a low temperature that it's not as practical because you have to use up so much energy to get it to be so low of a temperature that it's not practical. Like we can't have a super deep freezer to put our computers in, even though that would be great. So if it can be superconducting at room temperature, it would change society as we know it. And there's obvious in applications of you can have a magnetic train. You could have finally, like, who knows if we could have like flying cars. Before we couldn't have flying cars because it takes too much energy to levitate. But if you could levitate through magnetics because we had superconductors that didn't take a ton of energy just to keep it to levitate, then that would be crazy. We could finally have a world and a society that was just like the movies. We could have like flying cars, just really crazy stuff that we never thought was possible before. Our computers could be crazy, like without overheating and so many crazy stuff regarding that. But I think one of the biggest things is the implications for energy. So we know that the most wealthiest nations, they basically spend the most energy, and that's why they're wealthy. Um, and right now, a lot of it's in the form of oil. So whoever burns the most oil is like the pretty much the richest nation. Um, so that's not, obviously good for the society and from an environmental point of view. Um, but it also means that the winners like stay the winners because they're just using up all the oil. But if we could somehow have energy that is cheap, what would that mean? Like what is the implication for society, right?
Yeah, and we saw that a little bit. We got a taste of that with the whole Russia-Ukraine situation when Russia was one a large exporter of oil, and because they kind of people weren't buying oil from them, the price of oil shot up around the world. And so with that, we saw the price of everything pretty much go up. Because when you think about the global economy, a lot of things are shipped around and moved around. And to do that, you need oil. You need oil for the machines to make things. You need oils for the ship to kind of like transport things. And so oil is like kind of like the lifeblood of our economy. And
Yeah,
so, and right now, and oil is a limited energy source. And it's actually, I think we're coming to a point in society where we're kind of gonna be kind of tapping out on some of like
yeah,
there's gonna be diminishing returns in terms of like what we can extract in terms
yeah,
of oil. So there's
yeah,
concerns about oil prices continuing to go up. Like we're at the peak cheap oil period in this moment, and
yeah,
so
yeah,
that's why there's a race for new energy sources.
yeah, yeah. It's essentially like it's like the dinosaurs are working for us. It's basically like um, labor in a bottle is what oil is. And if we could,
Hmm.
get unlock that and get free energy, pretty much, virtually free energy, that would transform everybody, like every city, every place around the world would be completely transformed. Our, food prices would go down, everything would go down, and essentially the wealth of the entire world would go up very significantly if we could unlock this problem of energy. And people have been trying to solve the problem with something called a fusion reactor. And this is not to be confused with a fission reactor. So when we think of a nuclear reactor, we are actually talking about a fission reactor because there hasn't been a successful, sustainable fusion reactor created so far. And the reason why everyone's looking toward a fusion reactor is just the possibilities are, theoretically so much better to have fusion power than to have fission power. So the
Yeah.
sun,
What's the difference between the two?
yeah. So the sun actually uses fusion, um, and fission is basically means you're splitting it to get like splitting it apart. So you take a gigantic molecule like uranium or plutonium, and it has like a bunch of atoms together, and then you split that gigantic thing apart, and that releases an explosion of energy. And we capture that energy in a nuclear reactor and use it just to power our electrical lines. But a fusion reactor is going to combine two things. Instead of a gigantic molecule, it starts with something small, like typically deuterium, which is a type of hydrogen. So it's like one or two atoms, right? We're starting with like a very, very small thing, and you're like pushing the atoms together and combining it into one. So in the example of hydrogen, that's one atom, and if you can combine it together into one, that's also going to release a lot of energy, and in some cases, a lot more energy than fission. So, um, what's the implication? Well, if you split apart uranium like these gigantic things, there are like after effects of having a nuclear waste, right? And then you have like things that are continuing to split apart and through something called a half-life, and all that stuff that can kill us. Radiation and all that stuff can kill us. So it's obviously a bit of a problem with fission. But if you had fusion, what happens when you combine just hydrogen and hydrogen? You get helium. I mean, you don't really get much of a um, after effect. It's not that big of a deal if you do fusion. So that's exciting. Another thing that's exciting is um, the plenty like there's a lot of hydrogen in the world. Like majority of the world is water, and it's very easy to take water and make it into hydrogen. It's basically unlimited. There's not that much uranium in the world, so and like the byproducts are really dangerous. So if you could basically use water to get energy, unlimited energy, then essentially we could do anything we want because we have plenty of water in the world. And energy would be unlimited. So that's why it's the Holy Grail. What are the challenges of this? Is that the reaction is completely different. From splitting something apart is very different from combining it together. And right now, people are approaching this from the perspective of like magnets, because if you have a hydrogen atom, it's very hard to get this tiny little thing to like mush together with another hydrogen atom. Like they don't want to just mush together. This doesn't happen naturally, right? You're basically recreating the conditions of the sun on Earth, and if you can do that, you can unlock the power of the sun on Earth, right? So it's very exciting if we can do it. But right now, scientists are saying, hey, I'm dumbing it down a lot, but if you can basically levitate it or like basically keep it in between through magnets and then start shooting it around and make it go faster and faster and faster. And then at the very last moment, you can combine it together, then you would actually combine it and it would fuse into one in a fusion reaction. So in order to get that to work, you have to have very, very powerful magnets in order to keep that in the middle to then combine it together. So why is this a big deal? It's because the magnets are so powerful. You have to get so much energy to get it to stay in the center. And it takes a crazy amount of energy to do that. So yes, fusion will, it will change the world, but it's very, very difficult to get the magnets to do that. And that's why people are using thinking about using superconductors. But right now, as we know it, there is no proven superconductor that is at room temperature. And people have to spend so much energy and they have to use liquid nitrogen and all the stuff to try to get the metals to be cold enough for it to be superconducting to get the atom in the center. So if we had a room temperature superconductor though, you don't have to spend a bunch of energy. Like basically we spend energy to get our refrigerator cold, right? But you don't
Yeah.
have to spend energy to like make energy. That would be
Yeah.
a crazy unlock if we can basically efficiently keep the atom in the center so that we could attempt to get it to combine. And what would that has huge implications for society if we could get it, room temperature superconductor, because then we are that much closer to getting a working fusion reaction and a working fusion reactor.
Got it.
Yeah.
So basically, like, because we want the promise of nuclear fusion is interesting because it can make energy so cheap. But right now, to have a nuclear fusion, it actually costs a lot of money because it takes so much money to make everything the temperature is cool enough where these superconductors can do their work, and conduct and make that fusion happen. And so you're kind of like shooting yourself in the foot in trying to make cheap energy. You're spending a lot of energy, so the net cost is actually really still like very high. And
Yeah.
so the room temperature superconducting would be a total game changer, and that it would bring the cost to make the nuclear fusion happen. That reaction to happen would be a lot cheaper.
Yeah. Yeah. So, the people might think like, oh, well, what's the big deal of like unlocking magnets, essentially, right?
Yeah.
And it's a huge deal. There's so much technology that is based on magnets. Fusion is just one of them, but a lot of like the lost energy, like when we go from point A to point B, it's because of friction. Um, but if you can get rid of friction, right? You can get rid of friction. It just takes a lot of energy to get rid of friction. So when we have magnetic trains right now, it levitates, but it takes a bunch of energy to get the thing to levitate. You have to spend electricity to get it to levitate. But what if it
Mm-hmm.
could naturally levitate without spending energy? It's just
Mm-hmm.
because of the magnetism, right? That's actually possible if you had a superconducting material, but the problem is right now we've only known of superconducting materials at like really, really low temperatures. And that also takes a lot of energy to get things that cold, like way colder than freezing point. Um, and then what's the point, right? It still takes a lot of energy to get the thing to levitate. That's why we don't
Mm-hmm.
use superconductors on high-speed trains, and we just use energy. But then if you don't have to use energy at all and it just levitated, that would be crazy. Like we would see so many more applications in the area of transportation, in the area of generating electricity, in the area of computing. We think it's crazy now, but imagine what happens if you had a superconductor in the realm of computing. AI would go crazy. Like the types of computers that we could have would be insane. All the limitations that are based on energy that have to do with computing, like it overheating and all that stuff, they would all be gone. And then what would happen if our computing power became 100 times stronger than it is right now? And what kind of discoveries would be possible? Yeah, it's a very exciting time that we're in right now.